In the previous video, we explored the neuroelectromagnetic forward problem. In this video, we will delve into the neuroelectromagnetic inverse problem, also known as neuroelectromagnetic source reconstruction. We will take a closer look at the general concept of inverse problems, with a specific focus on the electromagnetic inverse problem. Following this, we will define the neuroelectromagnetic inverse problem and discuss the regularization-based solutions for addressing the nonlinear, ill-posed nature of these problems. The primary objective here is to reconstruct the neural sources responsible for the signals recorded by EEG or MEG. These signals, measured by the electrodes, will be traced back to determine which neural activations led to the observed data. Since neuroelectromagnetic source reconstruction is an inverse problem, we will begin our presentation with an introduction to the anatomy of inverse problems. Inverse problems involve the challenge of determining unknown causes from observed consequences, using predictive models, referred to as forward models, that link causes to consequences in a causal sequence. Forward models are typically well-posed, meaning that causes determine consequences uniquely and stably. In contrast, inverse problems are usually ill-posed, meaning the data may be insufficient to unambiguously identify the cause, an exact solution might not exist, and much like solving a mystery, discovering the cause without additional information is highly sensitive to measurement noise and modeling errors. On the left side of this slide, we depict both conventional and advanced inverse problems, highlighting the role of estimation theory in incorporating extra information. Generally, the Bayesian methodology provides a versatile and natural way of incorporating extra information to supplement the noisy data by modeling the unknown as a random variable to highlight the uncertainty about its value. Presenting the solution in the form of a posterior distribution provides a wide range of possibilities to compute useful estimates. Inverse problems are traditionally approached from the point of view of regularization, a process whereby the ill-posed problem is replaced by a nearby well-posed one. While many of the regularization techniques can be reinterpreted in the Bayesian framework through prior design, the Bayesian formalism provides new techniques to enrich the paradigm of traditional inverse problems. Inaccuracies and inadequacies of the forward model are naturally handled in the statistical framework. Similarly, qualitative information about the solution may be reformulated in the form of priors with unknown parameters that can be successfully handled in the hierarchical Bayesian context. Additionally, we illustrate the criteria for well-posed and ill-posed inverse problems. A well-posed, stable problem is characterized by the fact that a small perturbation in the data results in only a small change in the scattering parameter upon inversion. However, if any of Hadamard's three conditions are violated, the problem is deemed ill-posed. In the middle row on the right side, a schematic illustrates how violating Hadamard's conditions leads to ill-posedness. For instance, a perturbation in the data can result in a non-unique reconstruction. An unstable reconstruction occurs when the parameters differ significantly, even when the differences in the data are small. Non-existence is a situation where the reconstructed parameters fall outside the range of physically acceptable values. At the bottom, there is also a schematic illustration showing how incorporating prior knowledge stabilizes the inversion of data. After introducing the inverse problem and discussing the characteristics of the operators involved, we will now shift our focus to inverse electromagnetic problems. In electromagnetic imaging, particularly for brain imaging, the problem is often approached as a combination of source and scattering problems. Electromagnetic brain imaging devices use multiple antennas to transmit and receive high-frequency electromagnetic waves into the brain, which interact with brain tissues, and the scattered field will be received in antenna. These interactions cause scattering due to differences in the tissue's electromagnetic properties. In scattering theory, the problem is described by the Lippmann-Schwinger integral equation, which relates the total field to the incident and scattered fields. The scattered field is expressed as the integral of the source, Green's function, and contrast function, which forms our forward model. To solve this problem, we employ an iterative method that utilizes the Born approximation at each step. During the kth iteration of this method, the total field ATOC-1 is computed for the contrast function K-1 obtained in the previous iteration, using the state equation. By substituting ATOC-1 into the data equation and applying the Tikhonov regularization method, the optimization problem is solved to obtain K. For the first iteration, K0 is chosen arbitrarily. The slide presents the formulation associated with this solution, including the closed-form solution. Additionally, a simpler qualitative approach, known as source imaging, can be used to solve the inverse scattering problem. In this approach, each scatterer within the brain is treated as an electromagnetic point source emitting high-frequency signals. The bottom of the slide illustrates this simplification, showing the confocal or backpropagation approach used to demonstrate the scatterers. The formula is applied to the set of measured difference field data ES to retrieve a qualitative indicator function Q, which provides an initial estimation of the location and size of the detected scatterers inside the head. In conclusion, neuroelectromagnetic source reconstruction, which conceptually resembles qualitative methods, focuses on identifying internal sources within the brain at lower frequencies or in the electromagnetic spectrum. In the context of the inverse neuroelectromagnetic problem, the core challenge is to estimate the brain's neural sources, e.g., current dipoles, that produce the observed signals in EEG or MEG data. Mathematically, the problem is typically framed as y equals L dot theta plus epsilon, where y represents the observed EEG MEG data, measurements at the sensors, L is the lead field matrix, or forward model, that describes how each potential source contributes to the signal observed at each sensor. Theta is the source configuration vector representing the strengths and orientations of the sources, and epsilon is the noise or error term accounting for measurement noise and modeling inaccuracies. The inverse neuroelectromagnetic problem involves solving for theta, given y and L. This is challenging because L is typically ill-conditioned, leading to multiple possible solutions for theta. Due to the ill-conditioned nature of L, there are generally multiple possible solutions for theta. This makes the problem ill-posed, meaning small errors in y or L can lead to large errors in the estimate of theta. To overcome the ill-posedness, regularization techniques or constraints are often applied. In this point of view, methods to solve the inverse neuroelectromagnetic problem can generally be categorized into dipole models and distributed models based on how they conceptualize the neural sources, as illustrated in the schematic. Dipole model-based methods assume that the brain's neural activity can be represented by a small number of discrete dipoles, each with a specific location, orientation, and strength. In contrast, distributed model-based methods assume that neural activity is spread out across a large region of the brain, with the goal of estimating the continuous distribution of sources. Various methods, including Bayesian analysis, ECD, MNE, and beamforming, offer different ways to solve theta, each with unique strengths suited to different scenarios. The choice of method in practice depends on the nature of the data, the assumptions about the sources, and the desired properties of the solution. Each method may yield different estimates of the neural sources, so selecting the appropriate approach is crucial and often informed by the specific research or clinical context. Classic dipole models like ECD and music are designed for scenarios involving a small number of discrete, well-defined neural sources, while distributed models like MNE and beamforming focus on continuous source distributions. On the right side of the slide, we present 4 of the most common methods. The Bayesian approach solves the posterior distribution by combining prior knowledge with the likelihood of the observed data, typically maximizing the posterior map estimation to provide a refined estimate of the source parameters. The equivalent current dipole (ECD) method assumes a small number of dipoles and fits them to the data by minimizing the error between the measured and simulated signals, using nonlinear optimization to find the best-fitting dipole parameters, location, orientation, and strength. Minimum norm estimation (MNE) minimizes the L2 norm, total power, of the source distribution, often with regularization to handle noise, providing an estimate that balances fitting the data while keeping the source configuration simple, minimizing overall strength. Beamforming constructs spatial filters to estimate the source activity at specific locations, optimizing for a directional response, with the solution being a set of filters that, when applied to the data, highlight activity in specific brain regions while suppressing interference from others. The ECD method is a powerful tool for localizing neural sources in the brain, especially in cases where the activity is believed to be focal and can be modeled with a few dipoles. The core idea behind the ECD method is to model the brain's neural activity as one or more equivalent current dipoles. Each dipole represents a small, localized region of the brain where electrical activity is assumed to originate. The ECD method assumes that the brain's neural activity can be effectively represented by a small number of current dipoles, each characterized by its location, orientation, and strength. Each dipole is a point source of current that can generate an electromagnetic field, which can be detected by EEG or MEG sensors. As illustrated in this slide, the ECD method typically employs nonlinear optimization techniques to find the best-fitting dipole parameters by minimizing the difference between the observed sensor data and the data predicted by the dipole model, which include the dipole's location, orientation, and strength. The ECD method is particularly effective when the neural activity is assumed to originate from a small number of well-localized sources, such as in the case of evoked potentials or responses to specific stimuli. However, the solution can be highly sensitive to noise and the initial guess for the dipole configuration. So here is the point to introduce the inverse neuroelectromagnetic problem, also known as inverse source reconstruction. The objective in inverse source reconstruction is to estimate the location and magnitude of neuronal sources inside the brain using EEG/MEG data. To address this, we use the EEG measured data to find the source parameters in an iterative method. In left side we brought the schematic of the iterative method based on initial assumption in fine model and updating coarse model. First, we define an initial model as a guess and solve the forward problem, which involves simulating EEG signals based on assumed neuronal sources, location and strength. Then, we define the inverse problem, which involves adjusting the source parameters to minimize the difference between the simulated and actual EEG signals. To reduce this error, we must solve the optimization problem. By using Bayesian analysis, we refine the source estimates, where according to Bayesian analysis, prior knowledge combined with maximum likelihood gives us the posterior probability. In Bayesian analysis, the initial assumptions or prior knowledge pertain to the possible locations and strengths of neuronal sources, which could be based on anatomical data, previous studies, or reasonable guesses. Using this prior information, we simulate EEG/MEG signals by solving the forward problem, which predicts what the EEG/MEG data would look like given certain source parameters. Likelihood estimation plays a key role in comparing the simulated EEG signals with the actual recorded EEG data, as the likelihood function measures how likely the observed data is given the assumed source parameters. Posterior calculation is then performed by combining the prior information with the likelihood of the observed data, which results in the posterior probability. This posterior represents the updated belief about the source parameters after considering the actual data. The optimization process involves iterating to find the source parameters that maximize the posterior probability, providing the most probable estimate of the neuronal sources based on the observed EEG data. The final output is a refined estimate of the source locations and strengths that best explain the observed EEG signals, considering both the prior knowledge and the actual data. The formulation and parameters of the Bayesian analysis are demonstrated on the right side of the slide. In this slide, we will demonstrate the process of source reconstruction using a simple model. The first step in Bayesian analysis is to derive the event model from the prior probability and maximum likelihood. To illustrate this, we use a model with a parameter theta, which has a constant and bounded prior probability that varies from min to max. In this scenario, the forward model is straightforward, where the data y are direct observations of the parameter theta. The noise on the data is typically Gaussian, with a standard deviation sigma, which shapes the maximum likelihood as a Gaussian distribution. We then calculate the event model by integrating the maximum likelihood over the range from min to max and multiplying it by the prior probability's magnitude. This model shows how the overlap between the maximum likelihood and the prior probability affects the event model, with the highest overlap occurring when the expected values of the prior and the maximum likelihood are equal. The event model decreases as the prior probability's width increases, indicating that less informative priors lead to a reduction in the event model. To further illustrate, consider a simple example where y represents EEG signals from a single electrode, which must be explained by a model involving two dipoles with known positions and orientations but unknown magnitudes. The unknown parameters are represented by the vector theta, and the forward solution is given by y equals Ly. If the noise in the signals is Gaussian, prior knowledge about the source magnitudes can be described by a bivariate Gaussian distribution. There are two key scenarios in event model formulation. First, when the response is fully known in advance, the event model equals the prior expected value probability. Second, when nothing is known, the event model is 0 for any data value. The same logic applies to posterior probability. It is a Dirac distribution when the response is fully known, or 0 everywhere when nothing is known. Finally, we will look at the graphs of prior knowledge, maximum likelihood, and the posterior probability model to understand how we determine the magnitude of the neuronal activity parameter. The minimum norm estimation method is designed to estimate distributed sources of neural activity across the brain, assuming that neural activity is spread out rather than localized to a few discrete points. MNE is useful for identifying distributed neural activity, such as in studies of sensory processing, attention, or resting state brain activity. It is particularly well suited for situations where the brain activity is expected to be spread across multiple regions. The goal is to estimate a continuous distribution of current sources across the cortical surface. MNE seeks the source distribution that minimizes the data term, which is the sum of squared residual and model term, which consider as penalty term of the source configuration. This corresponds to finding the solution with the smallest overall current strength that still fits the observed data. The minimization of the norm is often subject to regularization, which helps handle the ill-posed nature of the inverse problem by imposing additional constraints. The schematic of this constraints, which is the connection between data and model terms and objective function, is illustrated in this slide. Regularization techniques, such as Tikhonov regularization, are commonly used in MNE to prevent overfitting to noise and to stabilize the solution. The regularization parameter controls the trade-off between data fitting and solution norm, and the regularized MNE solution balances the fit to the data with the simplicity, or smoothness, of the source configuration. In addition, MNE is used widely for reconstructing neural source distributions from EEG or MEG data, aiming to find the simplest source configuration that explains the observed signals. Techniques like Lasso and Loretta build on this concept to address different assumptions about brain functionality. Lasso, least absolute shrinkage selection operator, is particularly effective for identifying sparse, focal sources due to its ability to impose a strong regularization, effectively zeroing out less relevant sources. On the other hand, Loretta, low-resolution electromagnetic tomography, provides a smooth estimate of neural activity across a larger region, making it better suited for distributed sources. To illustrate the impact of choosing the appropriate method, here we brought a scenario where two distributed sources produce identical MEG signals. One is very focal, while the other is spread across many gyri and sulci. If the true activity is sparse, Lasso would correctly pinpoint the focal source. If the activity is distributed, MNE or Loretta would more accurately capture the broader distribution. Therefore, selecting the right method requires considering whether a sparse or smooth source configuration is more probable, often necessitating additional independent information about the brain's functionality.